My name is Trinh.
I'm Tukina.
I'm Sherman Yaghmaee, and I'm Bhakta.
Okay, so today our group will be going over the background and motivation for our project, as well as the development, data analysis, and conclusion. Laparoscopic surgery is basically a new technique, or a relatively new technique, which allows the surgeon to use smaller tools to protrude into the patient's body. These tools in turn gives us smaller incisions, fewer scars, and are less invasive. This is advantageous because it allows the patient to recover much quicker. The problem using a laparoscope is that when the laparoscope is entered into the human body, there's a quick temperature change from the operating room to the high 98 degrees Fahrenheit body temperature. This creates fog, which now the patient or the surgeon cannot see out of the camera anymore. So the surgeon must remove the camera, clean it using a technique called thread, and then reinsert the camera carefully and then reposition it. This may take up to 20 minutes and happens several times throughout a single surgery process. Now, as you can see, this delays the surgery for a good amount of time and could create complications such as stroke, heart attack, and increased blood pressure. So our group saw this as motivation to remove this delay in surgery and to create a tool which eliminates that delay, or eliminates the fogging and the delay.
So our project had three overall parts, or three sections to it. The main one was building a solution that would prevent fogging and remove smudging. But before we could do that, we first needed a way to simulate the problem and so cause the fogging. So we needed a testing apparatus. After we had a testing apparatus, we had to build a laparoscope, something to test. And once we had that, we could finally get for our solution. So for our testing apparatus, we wanted to mimic the internal conditions of the body during surgery. And so we were told that the abdomen is inflated with about 4 liters of CO2 during the surgery. So we wanted our volume to be about 4 liters. Also, we wanted our internal temperature to be about 98.7 degrees Fahrenheit. And we wanted a relative humidity of about 50%. And so we did that by making our chambers out of PMMA. We used heating coils from exhausters to get to the optimal temperature. And we introduced moisture into our environment by connecting our chamber to an external humidifier. And so that's how we created our testing apparatus. For the laparoscope, we bought 10 millimeter thick stainless steel tubing, and we chose 10 millimeters because that's about the average size of a normal laparoscope. We attached a glass slide to one end that acted as our lens, and on the inside, just to see what's going on and see the fogging occur, we put a 7 millimeter USB endoscope. And with those, now that we had a testing apparatus and something to test, we started working on our solution for service.
Okay, as was before, there are two major problems with laparoscopic surgery. One is fogging and one is smudging. There are two ways to approach this. You can either approach this mechanically or chemically. The mechanical solution being applying some sort of wiping or spraying motion to remove the fog or smudging. A chemical solution is one where you coat the glass shield with some sort of chemical solution that will prevent fogging or smudging to slide down the shield. We found out that the best way to solve the problem is a combination of both. So we designed the Helios jet. The Helios jet incorporates both the mechanical and chemical solution. The mechanical part is a water jet that cleans the glass shield. And as you can see, here's an image of a cross-section of the Helios jet. Now we want to make this available to all surgeons. So we had to come up with a way where any laparoscopic device could use it. So we figured the best way to do this is have some sort of attachment that would go on the end of the laparoscope and the surgeon could use with ease. Water, there's a metal tube that's connected right here, this device. It will squirt water straight down the shield at an angle, covering the entire shield, and there's an outlet right here that allows the water to roll down. This is one of the key and most important parts of this particular device. Next is a chemical solution. We had to find some sort of FDA-approved hydrophilic substance. As you know, there are anti-fog cleansers for your cars, for your glasses. the lab equipment, but you can't use this within the body. So after looking through literature and talking with faculty, we found out that the best solution for this is using polyethylene glycol. It's a very, very hydrophilic substance, so it will not interact with the oils and the fat during surgical operations. There's a lot of interstitial fat that the glass can rub against, leaving smudges. So what PEG does, being really hydrophilic, it will not interact with those oils. In addition, PEG will interact very, very well with water. And as you can see from these slides, the top one is no PEG. These are measurements of contact angles with our glass shield. This shield has not been treated with PEG. The contact angle, as you can see, is very, very high. As you can see right here, very, very high values. The bottom one is a glass slide treated with PEG. The contact angles are a lot lower, meaning that the water droplet on this glass slide is interacting with the surface.
So now that we knew that our surface were coated with PEG and it was hydrophilic, we wanted to show that this does prevent fogging. So what we did is we had a non-PEG slide and a PEG slide sitting in ice baths. And we took them out of the ice bath individually and moved them over to our testing chamber, which was set up to body temperature and near 100% relative humidity. And as soon as we took the non-PEG slide out of the ice bath, it started fogging. And when we put it into the testing chamber, it was completely fogged, as you can see on your left side. When we took out the PEG slide, it didn't fog at all, and it continued not to fog in the chamber. So we also wanted to show that smudging doesn't have a great effect on the PEG slide as well. So we did a procedure where we smudged a non-PEG slide with ground beef. And as you can see, it smudged pretty well, and the surgeon would have to remove that out of the body so you would be able to see through there. And we did the same with the PEG slide. There's a little bit of smudging and residue on there, but there's not much. And this shows the PEG surface does not attach to this. Next, what we did is we want to quantify how effective our Helios jet is. So what we did is we took an image with our endoscope, but with the non-PEG lens. The first column shows before we smudged it. The second column is when we smudged it, and the third column is after we washed it. The red boxes indicate where we looked at, and we wanted to show the difference between the intensity levels in the black and white sections. And Parag's going to go over the data.
So as Parag mentioned, we used some allo code, and what we wanted to see is the sharpness of the image. And the way we did that was actually we took each image and looked at the intensity across a certain line across the image. So as you can see, this is the picture for smudge. So this is just the lens itself, no smudging, no treatment, nothing. And by the way, this is just no PEG slide. So just think about with having a PEG on the slide, the results would be a lot greater. So as you can see, there's a sharp peak right here, or it shoots up drastically. And once we smudge it, you can see that the peak there's no sharpness to the curve. And so with our jet, we can actually get clarity back in our image, and you can actually see that with our data right here. So in conclusion, we found out a few things. We know that PEG prevents the fogging, which is actually one of the main goals, and two, smudging, which is actually more important than fogging. Now, with the jet that we created for the laparoscope, we can actually rinse off any excess debris we have that the PEG might have in the lens that might have gotten stuck to the lens even with the PEG on. And so the combination, we can actually prevent removal of the laparoscope during the procedure. So for future development, we want to improve the end piece. The end piece is made out of ABS plastic, which was used by the 3D printer. All the laparoscopes are mainly used, they're made with stainless steel tubing. So we'd actually like to make the end piece out of stainless steel. We'd also like to decrease the size, the smaller the better, and also incorporate like a suction at the bottom of our end piece. So any water that's actually left on the lens, we can actually remove that. And also for the lens, we want to actually try different PEG derivatives, to see because there are better PEGs out there than compared to the ones we use. And also we want to test in very different solutions, or test different solutions. We just use DI water for our test, but we want to see if when we change the temperature or using saline solution, if that that works better to
So our acknowledgement, our team like to thank Dr. Park and Dr. Bullock and Dr. Rogers. Dr. Park was our advisor, and as well Dr. Bullock and Dr. Rogers helped us out with our project, as well as the graduate students on the right. We'd also like to thank the Loma Linda surgeons, Dr. Amy Schaeffler and Dr. John Arnold II. They were very helpful with this project as well. And we'd also like to thank the Department of Bioengineering because they gave us the opportunity to for us to have this project and the funding. So right now we'll go ahead and start with our demonstration of our tool. So right now, so this is the image output from our laparoscope. And Tejas is going to go ahead and fog it with, or smudge it with some ground beef. This is 30% fat content. As you can see, the image is foggy. You can no longer, you can hardly recognize what that is. It is. Now, Pirran, to go ahead and turn on the jet, and you can see the water is running. And once you stop, the image is almost restored to perfection. Okay. Oh, it's getting it.
Yeah, so the thing about, one of the improvements was to remove the water. And so the issue we're having maybe is actually getting all the water removed off the lens. So, I mean, with the PEG layer, we wouldn't even have this issue. So because of our limitations, we can use a PEG slide for this demonstration. But as you can see, like, the vision is actually restored partially on just using our jet, and then with the PEG, we even that. And then, any questions?
So how do you attach this PEG to the lens? It's non-covalent.
How do we test it?
How do you attach?
I go through a process called salinization, where we plasma treat the glass slides, and we salinize it with 4,4 butyl and then diisopropyl and ethyl. And this allows the attachment for our PEG to connect to the glass slide. It's an intermediate step. It's an intermediate compound that attaches our PEG to the glass slide.
So what's the density of the PEG attached to the lens? Have you measured it? The percentage is almost area. 30%, 30%, or 60%? Are you testing or
The way that we calculate if the PEG is, the way we really have to testing the PEG from the surface or not, it's just a contact angle test. So
angle is some degree of it.
yeah. So what we did is we took our glass shields and we went through intermediate corners. So once we pulled up the entire slide, we took an average. So if it was within, we can kind of assume that our PEG is on the slide based on those numbers. But we had no actual way of seeing what percentage. So we used we took a glass slide and then we took how much PEG did you use?
We used about 45 grams.
So for 5 slides, 6 slides, so 3 full glass slides. And even for the lens,
We can't exactly tell you like what percentage it is, but just by the contact angle, how it varies high or low, it gives us a good idea of how much PEG is on there. Because there were some sides that didn't have enough PEG and some sides had an extreme amount of PEG.
Right. So eventually you're going to even take
Yeah,
exactly, yeah.
with the tools that we have, it was
That's my class to standing and aspirin.
Oh yeah, it's also good.
Do you guys test how the insulated slide can be sanitized? Like, do you have to throw it out after use, or can you sanitize when you use it?
Yeah, so basically, the surgeon would have to throw it out after use and then send us back the NPs that we've developed, and then we would have to go ahead and attach a new lens on there and then send it back out to them.
All this goes here.
Yeah, yeah, just both. Yeah.
Even your
Oh, okay, yeah, and then make this difficult as well.
Any other questions?